Welcome to a journey through the cosmos, presented by Dark Sky Dive, unveiling the engineering marvels that conquer the most hostile worlds. Jupiter stands as the colossal king of planets, a swirling gas giant that dominates the dark and cold expanse of our solar system. It is not just the largest planet we know, but it represents one of the most dangerous environments humanity has ever dared to approach. Beneath those massive clouds and majestic beauty, Jupiter is surrounded by the most intense radiation belts ever recorded in history by astronomers. A human being exposed in that location would perish in just a few hours due to the sheer intensity of the energy. Even a conventional satellite, built with standard materials, would be completely destroyed and rendered useless within a matter of mere days. Yet, humanity decided to send a probe directly into the heart of that invisible storm, defying all the odds stacked against us. That courageous vessel is named Juno, a machine built not just to observe, but to survive where nothing else can possibly exist. Juno was not designed simply to gaze at Jupiter from a safe distance, like the many Voyagers that came before it. Most planetary probes are designed to fly by, snap a few photos, and stay far away from the lurking dangers. Juno is different because its mission requires it to fly directly through the radiation belts and get close to the clouds. It must approach the cloud tops and repeat that dangerous maneuver dozens of times throughout its long and arduous mission life cycle. This makes Juno less like a standard scientific probe and more like a survival machine built for a zone of death. The assembly of Juno takes place in absolute clean rooms, under the strict and constant supervision of NASA's top engineering teams. In this pristine environment, a single speck of dust is viewed as a major threat that could compromise the entire mission. Contamination could cause short circuits, so every single component is tracked to its origin and cleaned with obsessive attention to detail. But the biggest challenge is not the dust on Earth, but the cosmic radiation that awaits in the vacuum of space. From the very early design phase, engineers had to ask how an electronic machine could possibly survive such a hostile environment. They faced an environment where radiation could destroy semiconductor chips in minutes, rendering years of work useless in a heartbeat. NASA's answer was to encase Juno's electronic brain inside a fortress, a structure designed specifically to withstand the bombardment. Inside the spacecraft's main body lies a structure known as the radiation vault, a heavy shield against the invisible enemy. It is crafted from titanium, weighs nearly 200 kilograms, and completely encloses the most critical systems of the spacecraft. This vault protects the computer, the processors, and the main control systems from the intense radiation outside the metal walls. Titanium does not block radiation entirely, but it reduces the destruction to a level that the electronics can actually withstand. Every single bolt on this titanium box is calculated for position, tested for vibration, and verified for structural integrity. They are also tested in simulated radiation environments to ensure the shield will hold when it matters most during the mission. Juno does not use the most powerful chips available. Instead, it uses the most durable ones found in the industry. The processors on Juno are thousands of times slower than your smartphone, but they possess a high tolerance for radiation. Crucially, these chips do not easily suffer from bit flips, which are errors caused by charged particles hitting the circuits. In the Jupiter environment, a single high-energy particle passing through a chip could cause a calculation error or system failure. It could trigger a faulty command or cause the team to completely lose control of the spacecraft forever in deep space. Therefore, reliability is far more important than speed when designing for the harsh realities of the outer solar system. Juno does not orbit Jupiter in a perfect circle. It moves along an extremely flattened elliptical path designed for safety. It approaches very close to Jupiter for a short time, then moves away quickly to minimize its exposure to danger. This strategy helps reduce the time spent in the radiation belts, allowing the ship to escape after each close pass. However, This places extremely high demands on the control systems, the thrusters, and the navigation software guiding the ship. A small deviation could cause Juno to be trapped forever in the death zone, ending the mission in failure. Unlike previous Jupiter probes that used nuclear power, Juno relies on 3 massive solar wings to generate its electricity. Each wing is longer than a standard school bus, a necessary size to capture the weak sunlight at that distance. They must operate in an environment where sunlight is 25 times weaker than what we experience here on Earth. The solar wings are assembled individually, tested for vibration, subjected to deep freeze, and checked for radiation resistance. They must unfold perfectly without jamming and provide enough energy for the ship to survive the cold, dark space. When the main systems are ready, Juno enters the final assembly phase, where every piece comes together for the first time. At this stage, every connection is checked multiple times, as there are no more major design changes allowed anymore. There are no more risky experiments because Juno cannot be repaired once it leaves the safety of our planet. There are no astronauts, no maintenance missions, and absolutely no second chances if something goes wrong during the flight. Before launch, Juno is placed into radiation test chambers, where engineers simulate the harsh conditions it will face later. There, they blast it with radiation many times stronger than expected, observing where components fail and reinforcing weak points. The goal is not to make a ship that never fails, but one that fails slower than Jupiter's radiation can kill it. When Juno finally enters Jupiter's orbit, the factories on Earth have completed their mission and the ship is on its own. From that moment on, every decision belongs to Juno, every error is permanent, and every bit of data is a reward. Juno not only survived, but exceeded its initial design life, continuing to send back data that is unprecedented in history. Juno is not the fastest, strongest, or most complex probe, but it is a testament to human engineering and resilience. It proves that humanity can design for survival, even in the most deadly environments of our solar system's giants. And it all began with quiet hands working diligently in a clean room on Earth, dreaming of touching the stars. The legacy of Juno teaches us that preparation is the key to conquering the unknown challenges that lie ahead of us. As we look at this tiny machine against the giant planet, we see the triumph of intellect over the forces of nature. The data returned has rewritten textbooks, revealing a complex interior that scientists had only theorized about for many decades. We have seen auroras that dwarf our entire planet, powered by the very magnetic fields that threaten to destroy the ship. Flying over the poles, Juno discovered cyclones arranged in geometric patterns, a phenomenon never before seen in the solar system. These storms, the size of continents, churn in perfect formation, challenging our understanding of fluid dynamics on a planetary scale. Back on Earth, the team deciphers these signals, turning raw noise into clear pictures of a world we cannot visit. Before Juno, we thought we knew Jupiter. Now we realize we are just beginning to understand its true complexity. The magnetometer, placed on a long boom to avoid interference, has mapped a magnetic field lumpy and uneven in structure. This suggests that the dynamo powering this field is closer to the surface than we originally thought possible. As Juno crosses the line between day and night, it captures the lightning storms that rage in the upper atmosphere. These lightning strikes, originating from ammonia water clouds, are a unique weather feature that Juno was built to detect. Its microwave eyes peer deep below the colorful stripes, finding that the roots of these storms go down very deep. The Great Red Spot is not just a surface storm. Its roots extend hundreds of miles into the planet's interior. We have stared into the eye of this centuries-old storm and found warmth and depth that surprised the entire scientific community. By measuring subtle shifts in gravity, Juno searches for a solid core, trying to answer how our solar system formed. The data suggests the core is not a compact ball of rock, but a fuzzy, diluted mixture of heavy elements. This implies a violent history, perhaps a massive collision with another protoplanet during the early days of the solar system. Juno also turned its gaze outward, capturing the faint rings of Jupiter from the inside, a perspective never seen before. It has flown past the volcanic moon Io, witnessing plumes of lava that paint the surface in yellow and red. It has imaged the icy shell of Europa, providing data for future missions that will hunt for life in its ocean. And it captured Ganymede, the only moon with its own magnetic field, adding another piece to the Jupiter system puzzle. With each orbit or period, the spacecraft ages, its solar panels degrading slightly under the constant barrage of high-energy particles. Yet, the over-engineering of the power system means it still has enough energy to keep its heart beating and transmitting. The titanium vault has held the line, protecting the delicate electronics from the radiation that should have killed them long ago. NASA extended the mission, pushing Juno to explore the moons and the rings, going far beyond its original primary goals. A new generation of scientists now studies the data, building their careers on the stream of information Juno provides daily. From its vantage point, Earth is just a bright star, a distant home where thousands of people work to build it. We remember those hands in the clean room, the careful assembly, the rigorous testing that made this impossible journey a reality. Every diagram drawn and every calculation made years ago is now vindicated by the survival of the machine in space. It continues to dance with the magnetic fields, skirting the edge of destruction to bring us the truth about Jupiter. The radio instruments listen to the roar of the planet, a song of plasma and magnetic waves echoing in the dark. Through JunoCam, the public has joined the mission, processing raw images into art that reveals the planet's stunning beauty. This mission belongs to everyone, bridging the gap between high-level space engineering and the curiosity of people around the world. Having survived far more orbits than planned, Juno is now an old veteran, scarred but still standing tall and functional. One day the fuel will run out, and Juno will be commanded to dive one last time into the clouds. It will become part of the planet it studied, ensuring that it never contaminates the potentially habitable moons nearby. But that day is not today. For now, the spinner continues to rotate. The sensors continue to measure and record. It has beaten the radiation, conquered the cold, and bridged the immense distance to bring Jupiter closer to us all. The story of Juno is a masterclass in risk management, showing that with enough preparation, we can survive the impossible. This machine, built by human hands, stands as a giant among robotic explorers, a true warrior of the planetary frontier. Its success paves the way for future explorers to visit Uranus and Neptune, worlds that also hide deep mysteries. The technologies validated by Juno are already finding their way into the next generation of spacecraft, like the Europa Clipper. Solar power is now a viable option for the outer solar system, thanks to the trail blazed by this pioneer. The concept of the radiation vault has become a gold standard for any mission daring to enter high radiation zones. Jupiter remains a beast, a beautiful monster that does not welcome visitors. Yet we have found a way to stay. We found the gaps in the armor, the safe path through the storm, and we exploited them with mathematical precision. Mathematics and physics are the languages of survival here, guiding the ship through invisible minefields with absolute certainty. Behind the metal and the code, there is the sweat and fatigue of hundreds of people who dedicated their lives. That moment of arrival in 2016 was the culmination of years of planning, a victory for all humanity. Juno serves as our ambassador to the giants, a robotic extension of our curiosity and our desire to explore. It even carries 3 aluminum Lego figures, representing the connection between mythology, history, and modern scientific exploration. From Galileo's first look through a telescope to Juno's close-up dive, our journey has been one of constant discovery. We have come a long way from simple glass lenses to titanium vaults and solar wings spanning the size of basketball courts. Yet the spirit remains exactly the same. the burning need to know what lies beyond the horizon of our world. As long as the sun shines and the transmitter works, Juno will keep spinning, keep watching, and keep reporting back. There are still mysteries to solve. The abundance of water, the depth of the winds, and the true nature of the core. Juno will not rest until it has squeezed every last drop of knowledge from the gas giant's tight grip. The clean room where it was born is now busy with new projects. But Juno's legend will echo there forever. The lessons learned from its construction are now written into the engineering textbooks that train the next generation of builders. Students today study this machine to understand how to protect delicate electronics from the harshest forces in the universe. Juno is more than a robot. It is a physical manifestation of human perseverance and our refusal to accept defeat. It proves that no environment is too hostile if we are smart enough, careful enough, and brave enough to try. As it dips into the shadow and re-emerges into the light, it reminds us that knowledge always dispels the darkness. The faint sunlight it harvests is enough to power the discoveries that illuminate our understanding of the solar system. Jupiter is no longer just a terrifying monster in the dark. It is a world we are actively mapping and understanding. We have peeled back the layers of the king of planets, revealing the chaotic and beautiful machinery that drives it. Every image sent back is a masterpiece of art and a treasure trove of scientific data, cherished by the world. Juno has fundamentally changed how we view gas giants, not just in our own system, but throughout the galaxy. What we learn here helps us understand the thousands of other giant planets orbiting distant stars in the night sky. This mission is a crucial stepping stone, proving that we have the technology to explore the most extreme frontiers. We owe a debt of gratitude to the engineers, the scientists, and the dreamers who made this daring mission possible. They worked tirelessly in the shadows of clean rooms and control centers so that Juno could fly in the light. Juno stands as the ultimate survivor, a machine that looked death in the eye and refused to blink or retreat. The story of Juno is not yet finished. New chapters are being written with every orbit and every byte of data. Let this mission inspire you to keep looking up at the sky, to keep asking questions, and to stay curious. The universe is filled with wonders waiting for us, protected by dangers that we will eventually learn to overcome. Dark Sky Dive is committed to bringing you these incredible stories of human ingenuity and cosmic mystery every single week. If you enjoyed this deep dive into the engineering of Juno, please like this video and share it with friends. Thank you for watching this journey on Dark Sky Dive. Subscribe now to explore more secrets hidden within our vast universe.